All right, so this morning we want to talk about a form of spectroscopy that I think everybody who has studied chemistry has experienced in their first semester. And yet, as you'll see, it is one of the more complicated spectroscopies if you really want to start to wrap your head around it, and that is optical spectroscopy. And today I'm going to have this thing working. Well, let's see, famous last word. So I think in order to get started on spectroscopy, it's very important to understand the energy range of the photons that are involved, right? Because in every energy range of photon, there are different molecular phenomena that are triggered, and there is a hierarchy, an energetic hierarchy. And so in order for spectroscopy to not get chaotic, I think it's very good to use the energy of the photons that are involved as a guiding principle. So we start here with Mössbauer spectroscopy. These are nuclear transitions, so very high energy, then to X-ray absorption involving core level electrons, then to the optical region of the spectrum involving visible photons of a couple of electron volts, 1 to 4 electron volts. Then we go into infrared, that is a fraction of an electron volt, finally to microwaves and radio waves. And so the molecular phenomena that belong to that, I think, can broadly characterized into two groups. And these two groups are the following. And so these are, starting with optical spectroscopy's methods that involve a change in electronic configuration. So where you really start like moving electrons out of their orbitals and that they occupy and move them into partially occupied or empty orbitals. And so that is if you want, nuclear event in the life of a molecule, because you really change the bonding, you change the electron distribution, and you do something brutal to the molecule, right? And the other spectroscopies, everything that's happening here on this side is happening in the ground state electronic configuration, right? And so what you're doing here in vibrational spectroscopy, you're just triggering molecular vibrations. And then if there's not enough energy to do that, then you just like flip electron spins in EPR spectroscopy. And if you don't have enough energy to do that, then you just flip nuclear spins. But you have to be aware that everything that is happening here is happening simultaneously in all of the other spectroscopies and contribute to the line width that is just not resolved. But all of these molecular phenomena happen at the same time. So, but optical spectroscopy really is special. And why is it special then? So what's the range of photon energy here is like 1 electron volt through 4 electron volts. And so why do you think that's a special energy range? Any idea? Because that's roughly the same energy range as the energy of a chemical bond, right? So that is practically the energy of a chemical bond. That is the very reason why a field like photochemistry exists, right? Because you can really make bonds, break bonds, and form bonds with the action of light. And so it's the most direct way to study the chemical bond is really optical spectroscopy, absorption spectroscopy and all of its variants that we'll briefly look into. Yeah? And everything here, you look at the consequences of chemical bonding, but here you look into the chemical bond itself. And that makes it exciting, and that also makes it quite complex, and you'll see later what I mean by that. Let's briefly recap experimental techniques, and that is by no means an exhaustive list of the techniques that you can encounter in optical spectroscopy. The most elementary, of course, is absorption spectroscopy, like you have all experienced in your lab courses. And that is a basic technique that you essentially probably routinely run your molecule through, like during synthesis and after synthesis. There is a fine art that had been developed for a long time, and that is single crystal spectroscopy, where you really rotate a crystal and use linearly polarized light. That is an art form that unfortunately has vanished from the surface of the Earth. Nobody does that anymore, although there is a lot one could be learned, and there is a lesson to be had here. Then is so scientific communities, they they survive if they find an umbrella under which they can sell their science. And that has not happened with single crystal absorption spectroscopy. It has happened in magnetism, like the umbrella was their single molecule magnets, and it has happened in other fields, or now it's quantum computing or whatever it is, like that you can like paint on your forehead and say, look, that's what I'm working on. But the fact is that there is a lot of very high level scientific culture that has that has died because people didn't find an umbrella, and single crystal absorption is one of those. Now you can also use circularly polarized light and then measure circular dichroism, and that is assigned quantity. So you see there's a lot more structure here in the CD spectrum than there is in the absorption spectrum. And you can take that a step further and apply that in the presence of a magnetic field, and then you go to magnetic circular dichroism. That's one of our specialties here in Mülheim. And so that's basically a three-dimensional experiment, because you have the wavelengths of the radiation, the temperature, and the strength of the magnetic field. And that's a very powerful technique that we'll talk about on Thursday. Now you can also measure vibrations in the optical region by shining a laser into an absorption band, and what you'll see is then that the stray light, the inelastically scattered radiation, contains vibrational information, but it also contains a lot of information on the nature of the electronic state that you're exciting, and Maurice has talked to you about that. And finally, Serena, after this lecture, will talk to you about X-ray absorption spectroscopy and all the wonders that you can do with it. So let's briefly get like a very high level, so to say, like a very coarse overview of the kind of electronically excited states that you meet in transition metal complexes, and then I go on to relatively long detour about the nature of electronic states in general. So if you look at the molecular orbital diagram of a transition metal complex, it typically looks like that there are, in case of a D metal, the 5 molecular orbitals that derive out of the metal D shell that are partially occupied. And then you have occupied ligand orbitals, say of ligand 2 and ligand 1, and then you have empty ligand orbitals, often when the ligand has a pi systems like pi star orbitals. And so you can classify the excitations that happen in a transition metal complex broadly as DD excitation, that is moving electrons around in the D shell. Then ligand to metal charge transfer transitions, when you move an electron out of a doubly occupied ligand orbital into the metal D shell, or an MLCT, a metal to ligand charge transfer excitation, if you move an electron out of an occupied metal orbital into an empty ligand orbital. Then there are also, of course, intra-ligand excitations, where you move electrons within from an occupied ligand orbital into an empty orbital of the same ligand. That is very prominent. So in porphyrins, for example, the most of the excitation spectrum that you see in a porphyrin is actually the intra-ligand excitations of the porphyrin ligand itself. But if you have several ligands, there are also ligand to ligand charge transfer transitions, and these are very prominent, for example, in metal radical assemblies. So there is a lot to play with, and one way to visualize these different excitations is to draw yourself electronic difference densities. So that is then the electronic density of the ground state minus the electron density of the excited state. Yeah, and so let's say now red is the region where electron density is gained in the excited state, and yellow is where electron density is lost in the excited state. Yeah. So for example, here you have a DD excitation, and you see from the electron density difference that very little is happening here in the region of the ligand, but there is a redistribution of electron density here in the xy plane, and so you can see from the shape of that must be an excitation from a dxy kind of shaped orbital into a dx squared minus y squared shaped orbital, because it goes along the ligands here. And for an LMCT transition, it is clear that here's the position of the ligand. Let's say that's a halide, for example, chlorine or bromine or something. And there's a lot of electron depletion at the site of the ligand and a lot of electron gain here at the position of the metal. And for an MLCT transition, it's just the way around. It's a bit messier. So here you have the electron loss at the place where the metal is, and then you have the electron gain here at the position of the ligand, and that's clear that is a transition into a pi star orbital of the ligand. And a ligand to ligand, or like an intra-ligand excitation, you see that all of the electron density changes are happening at the ligand. So that is something that is a nice visual. And in a moment I will explain to you the difference between an electronic difference density and a transition density, because I think that's very important. Let's now get to a few practical aspects that are that I personally find important to to emphasize, and that have to do with assigning optical spectra, because you once you go into the literature, you will see all kinds of crimes that people commit in the assignment of optical spectra or the lack thereof. So let's do that systematically and first talk about the data reduction. And so from the raw spectrum to the Gaussian fit. And the first very common mistake, I'm not sure if I should call it a mistake or a bad habit, is to plot optical spectra on a wavelength scale, right? And so the spectrometer, of course, scans wavelengths, and then it gives you basically a table of wavelengths versus absorption. There is nothing wrong with that per se, but you have to realize that the wavelength is inversely proportional to the photon energy. But the molecular phenomenon that we're looking at, the absorption of photons to reach excited states of the molecule, that is linear in energy. So you're grossly distorting the molecular phenomenon by plotting it over something that is inversely proportional to the energy. And the effect is the following. So let's look here at the spectrum as it should be plotted on a scale that's linear in energy. Right? So, for example, wave number is linear in energy, or electron volts would be linear in energy. Yeah. So, and the connection between wavelength and wave number is just 10 to the 7 divided by wave number gives you wavelength, and vice versa. So what you see here is that basically all of these bands on the energy scale have the same width, roughly speaking, and that is generally true with a few exceptions that I'm going to explain to you later. But by and large, in most molecules, the width of absorption bands, when you plot it properly, is not varying dramatically. So now, of course, when you plot that on a wavelength scale, you will find that those that are at long wavelengths, meaning small energies, they get artificially broad, because a certain increment in wavelength corresponds to a large increment in energy, and vice versa, right? And those that are here in the UV region, they get artificially small. And that is also when you start comparing theory and experiment, and you say, I'm only 10 nanometers off, right? 10 nanometers off here is a very large error. 10 nanometers here is a very small error, right? And so please do me one favor. If you're serious about like calculating or assigning or analyzing optical spectra, the absolute first thing you have to do is to plot it on a proper energy scale. Yeah. Okay. So because spectroscopy happens in energy space, you have a similar issue in EPR spectroscopy, where you plot a long magnetic field that is also inversely proportional to energy. Yeah. Then the second thing you really should do is to not plot just basically absorbance, but to go the extra mile and know the concentration of your sample and to know the path length, and then convert that to extinction coefficient so that you actually can plot the spectrum on a Y scale that is per molar and centimeter, because that is something that you can also relate to. And the So when you analyze or assign spectroscopy, the energy at which a transition occurs is important, of course, but it's only half the information. And the other half that is usually more important and more telling of what's happening in the molecule is the intensity of the transition, right? And so what you really should do is to make an effort to get proper intensities. Yeah? And the proper intensity is then not the height of the peak, but is the area under the peak. Yeah? And so what you have to do eventually is to resolve the absorption spectrum into individual bands. So you often fit Gaussian bands. That's not the only line shape that you can use, but you will often in real life molecules fit Gaussians. And there is a golden rule there: never put a Gaussian where there isn't at least a peak or a shoulder. Then is right. That is important, because you can fit a square elephant with Gaussians, right? Then is absolutely no problem. And so you see here there is no Gaussian where there is no peak or at least a shoulder. And once you have done that, then you integrate the area under each Gaussian. Yeah, so basically that is that integral here of the extinction coefficient in molar and centimeter integrated over wave number, and you multiply that by the magic number 4.32 times 10 to the minus divided by the refractive index of the solvent that you're using, and that gives you the so-called oscillator strength. And the oscillator strength, that's something that your favorite quantum chemistry program will output for you, and that is something that you can then compare to experiment, right? So very important. Then it's don't sleep on the intensities. Yeah. And so there are a few simple steps that you as the experimentalist have to do in order to do that right. Now, of course, in order to properly Gaussian resolve the absorption spectrum is an unsigned quantity, right? And it can be pretty broad and it can be pretty featureless, and the larger your molecule gets, unfortunately, the broader the spectra get, and the harder they are to resolve into individual Gaussians with a great deal of confidence. That's why it's great, even if you couldn't care less like why things are positive and negative, to measure alongside the absorption also the CD spectrum and the MCD spectrum, because they give you so much more structure. And then you should perform a simultaneous Gaussian fit that fits all of these spectra simultaneously, where you keep the position of the Gaussian constant throughout all of the spectra, but the intensities can vary. Yeah? And so whenever there is a shoulder or a peak here in any of these spectra, you're allowed to put another Gaussian, right? It may well be that the transition that gives rise to that shoulder here doesn't really prominently show up in the absorption, but you have clearly identified it in the CD, and then that's okay. Yeah. And so that is essentially the job you have to do if you take it seriously, right? Like if you don't take it seriously, that's okay too. Yeah, you just use the absorption as an analytic tool or as a fingerprint. That nothing wrong with that. But now we're talking about the hypothetical case where you do take the absorption spectrum seriously and you want to learn something from it. Yeah, and then these are the steps you have to do. Yeah. Okay, and that means after that, that is, and notice how I haven't talked about orbitals, states, transition moments, nothing. This is just simply the experimental facts. That is as much as nature is willing to tell you. Yeah, and that is very important. I will keep coming back to that, because that is the primary unbiased data. And in science, you should always separate the facts from the fiction, right? So don't jump to conclusion what any of that is unless you have done a proper analysis. So the primary result of the analysis, you have your molecule, and you as a synthetic chemist, you have gone out of your way to make sure that that's a clean compound and that the absorption spectrum is really reflecting your compound and not any impurity or whatever it is. And then you put the results in a table. And that's a table that looks like that. So here are the transition energies. These are the centers of your Gaussians. These are the widths of your Gaussians. That's the oscillator strength. Then in CD you would have the intensities expressed as so-called Kuhn anisotropy factor, and in MCD it's expressed as the so-called C over D ratio, and explain later what that is. Full stop, period. That's it. And then you can move on to the next section of your paper and start analyzing what all of this stuff might be. And in order to do that, we need to take a slightly deeper look into electronic states. And that easily can get a bit scary. So if you find what I'm telling you next a bit overwhelming, don't be disheartened. Then is because that's something that took me years to appreciate, and most people take some time before they can wrap their head around and it. And it's at the end of the day, once you got it, you really get it, and that's a big asset. So now let's look at the one thing that is more important than anything else to understand about electronic structure, and that is the difference between states and orbitals. So what is a molecule? So let's be a physicist for a moment and say, what's a molecule? And so to a physicist, a molecule offhand is nothing else but a collection of electrons and nuclei. And these nuclei are point charges. For almost all of chemistry, it's good enough to treat the nucleus as a point charge. And so the one thing that's happening here is electrostatics. So like charges, positively charged nuclei repel each other, negative charged electrons repel each other, and nuclear electrons attract each other. And the one thing you have to add to it is the kinetic energy of the electrons, because within the framework of the so-called Born-Oppenheimer approximation, our nuclei are assumed to be at rest, and the electrons can follow any movements that the nuclei make simultaneously. To me, it was always magic, then, is to think that there is basically a single physical law that is explaining almost all of chemistry. And that's largely true. And the one thing that stands between us and from this picture going to all of chemistry is quantum mechanics, right? But if you go through the pain of doing that, it really deep down is that simple. But it's not really simple, right? Then it's because in Newton's times, when they were studying planetary motion, they already realized that they cannot, in closed form, exactly predict the motion of 3 planets at one time. So that's a famous 3-body problem, right? And in quantum mechanics, there is no closed solution for a 2-body problem. And in relativistic quantum mechanics, there is no closed solution for a 1-body problem. And in quantum electrodynamics, there is no closed solution for a no-body problem. And that is how progress in that field went. Yeah? But deep down, I think it is quite reassuring that we live in a world that is essentially governed by a single physical principle, and that is Coulomb's law. All right, so what quantum mechanics tells you, that this collection here of charges in motion can adopt discrete energy states. Yeah, and so basically we can put all this in a so-called Hamiltonian. That's the operator for the total energy, and that has a certain spectrum, right? And that spectrum here, I've drawn here vertical lines. That spectrum is the true eigenspectrum that a molecule at a given configuration can have. Yeah? So these are the electronic states that can happen. And that is the one and only thing that you can observe. Yeah? And that is very important. It's the entire state of the molecule. Yeah? So in this state, the motion of all of these charged particles is one way, and in this one there is another way, and in this one there is yet another way they move, etc., etc. But it's always like the collective state of all of these particles that is at stake. Yeah? So if I wanted to express that formally, then the Schrödinger equation is the action of that many particle operator, the Hamiltonian, on a many particle wave function, right? And it contains the coordinates of all of these n electrons. So we have n electrons in the systems, and each electron has a position and a spin. Yeah, and that is the many particle wave function. And the many particle wave function, the interpretation of it is is that the square of that wave function is the probability of finding electron 1 at position R1 with spin sigma 1 at the same time electron 2 at position R2 with spin sigma 2, etc., etc. So that is the absolute maximum that quantum mechanics allows us to know about a molecule, right? It's way more information than we ever need, but that is essentially the exact non-relativistic Schrödinger equation. Yeah, and the one thing I have to add to it, then if I want to make it complete, is to add relativistics and external fields. Okay, but that spectrum here, that has, as I've drawn in the previous slide, a certain number, an infinite number of discrete energy level. And that is the only thing that any experiment can probe. And if you read a paper where they have observed orbitals, then you can rather sharply conclude that these people don't know what they're talking about. Then it's because that is wrong. Yeah. So now, as long as there is no spin in the Hamiltonian, the total spin of the system, that is, I will talk about at some length further, that is a good quantum number as its projection on the z-axis. Right? Once you include all of this, there are no good quantum numbers anymore. Now compare that to what you get in, say, Hartree-Fock or DFT, what Dimitrios has told you about, where you replace that many-particle Hamiltonian by an effective one-particle Hamiltonian, the Fock operator or the Kohn-Sham operator, that is only operating at the coordinates of one electron at a time. And that operator also has a certain spectrum, yeah? And that certain spectrum is the spectrum of one-particle energies, and these are orbital energies. So now it's important that these orbital energies, the spectrum of orbital energies has nothing to do with the spectrum of the many-particle Hamiltonian, right? And so, for example, the Kohn-Sham or Hartree-Fock equations, they can be converged on different electronic states, right? And then each and every electronic state has a totally different one-particle spectrum, yeah? And so, to get that clear, right, you cannot observe orbitals, you cannot observe orbital energy differences. They literally are only interpretation aids, like as I told you on Sunday, but they have no rigorous physical meaning, right? They are intermediate quantities in a calculation that is approximating many particle states and many particle energies. The only observable quantities exclusively and only derive from the many particle spectrum of the Hamiltonian. Let me give you an example. So here is an iron-sulfur cluster. And a few years ago, we went through some fairly high-level quantum mechanics, and I've calculated the many-particle spectrum of a number of spin states of that thing. And so they're here in black. And now you can compare that spectrum of many-particle states to, say, the one-particle spectrum that, say, DFT delivers for the high-spin state or for the broken symmetry state. And you see there are no commonalities. It has nothing to do with each other, right? So there is nothing observable that you can confidently derive from looking at the one-particle spectrum, yeah? And our friends in physics, they often talk about, like, say, they unfortunately have a different nomenclature, and in that nomenclature they call orbital states. In chemistry, that's a mistake. It's just simply wrong, right? And so in physics, there exists something like as a density of unoccupied states. That cannot, that's a phrase that in chemistry has no meaning, right? Because a state cannot be occupied or unoccupied. A state is a state. It's one of those things, one of the possible states that a molecular system can assume, but it can't be occupied or unoccupied. An orbital can be occupied or unoccupied, but if you scramble the language to the point where you don't make a difference between orbitals and states, then you get confused, right? And I'm like overemphasizing that difference so strongly so that you are able in your mind to divide what is a many-particle quantity and what is a one-particle quantity. I love orbitals as much as you do and anyone else, right? But you've got to be clear what the status of it is. Let me give you one rather extreme example from X-ray spectroscopy. Let's say you have a sextate S-state ion, so high-spin D5 system, and so in the ground state configuration you have a 2p6 and 3d5 configuration. All right, and now you make an LH excitation in which you move one electron from the 2p shell into the 3d shell, going to 2p5, 3d6. All right, and so you have 15 particle hole pairs, right? That would give you, say, if you like, in an orbital picture, there are 15 possible excitations. And guess how many states you really have? And the number is 1,512. So there are 1,512 electronic states that arise from that single excitation here. And all of them are observed in the experiment. Yeah? And so now you can try to take 15 particle hole pairs and describe 1,512 states, and the result will be a disaster, right? Something that has nothing to do with experiment whatsoever. And that's what you get, for example, in TD-DFT, absolute fiasco, because that's a particle hole theory, right? Yeah, so that is the actual many particle spectrum for that LH excitation, and you see it's a dense spectrum. You can give names to each and every one to these states, and that is what TD-DFT would give you, just like 3. Then, well, and that's it. Yeah, and so please be aware that like orbitals and states are not the same. But of course, orbitals are very useful quantities in order to construct states. But that is an approximation, right? So you could do all of quantum chemistry theoretically without ever touching the word orbital. Yeah? For example, the first calculations, accurate calculations on the helium atom, were done in the so-called Hüllerrath formalism, in which there are no orbitals. There just is a 2-electron wave function, and the 2-electron wave function has some ridiculously complicated mathematical expression to it, but there is no orbital. So orbitals aren't real, then it's right. They're auxiliary quantities that help you understand. And once you get that, once you do not only find that hostile for me to say that, but you accept that that's the way it is, you can make wonderful use of orbitals. And let's practice that. So here's now how you go from orbitals to states. Now that is an MO diagram for like some molecule in a certain symmetry. For example, here is C2V symmetry, and then you give each of these orbitals you assign to the irreducible representations, as Serena has talked to you about. And in order to not get confused, my personal rule is I always give lowercase letters to 1-electron quantities and uppercase letters to many electron quantities, then I never get confused what it is that I'm talking about. So now you have the orbitals and you have given them numbers, and these numbers are that is the running index and that is the irreducible representation. So 1A1 is the first orbital of A1 symmetry, and then you have the second orbital of A1 symmetry and the third, etc. And then you start filling electrons in, and an electron configuration then is simply the distribution of electrons among the orbitals. So these are expressed as occupation numbers, right? So the occupation number is basically a vector, and this vector has entries 0, 1, or 2, right? Like for an empty, singly occupied or doubly occupied orbital, right? Okay, now you have to find out what the total spin is. So in that diagram, you may have a number of singly occupied orbitals, and they couple to a given total spin, and I will talk a lot more about on the next slide. But that total spin is then having the quantum number S and the spin projection quantum number M. Yeah, so that's a proper Clebsch-Gordon series. And one way this is not done is to say, oh, here I have a spin of 1/2 and here I have a spin of 1/2, so my total spin here is 1. That's the way I've drawn it here. That's the way that normally people do it, but that's not the full story. Yeah. And then you have the total symmetry of the state, right? And the total symmetry of the state derives from the direct product of the symmetries of the singly occupied molecular orbitals, right? So the doubly occupied orbitals always contribute the totally symmetric representation, and a partially occupied shell then the direct product of these orbitals. That gives you the total symmetry of the state, right? And so basically you arrive at a representation of that state that has a capital psi, because it's a many electron state. It has a total spin quantum number S. It has a magnetic spin quantum number M. It has an irreproducible representation gamma. And then you need some kind of running index, because there will be many states of a given symmetry and total spin. Yeah? And if you want to, you can also attach that occupation number vector to it. Let's take a practical example that is now the water molecule. And here are the occupied valence orbitals of the water molecule. Here's an A1 orbital that is B2, 2A1, 1B1, right? And so these have familiar shapes, and they're like lone pairs on the oxygen here, and CaOH bonding orbitals. And here are the empty orbitals, and you see they're having more nodes. And these are the orbital energies that you would get from a Hartree-Fock calculation. And so that distribution of electrons among these orbitals, that gives you the 1A1 singlet A1 state. Yeah? And you arbitrarily put that to 0 electron volts. You can also put it to minus 10 million electron volts or to plus 10 million electron volts. That doesn't matter, right? Because everything else is measured relative to the energy of the ground state. Now, the first excited state that you meet is by taking an electron out of the highest occupied molecular orbital, moving it into the lowest unoccupied orbital, and flipping its spin. And so that gives you the 1 triplet B1 state. And it's at 7.11 electron volt. And notice how that is not the orbital energy difference between these orbitals, right? And the next state that you meet is the corresponding singlet state, where you flip the spin of that electron, and that happens to be higher in energy, 7.62 electron volt. And that's quite typical, like for a given excitation, at least in a closed shell system, there's always a pair of singlet and triplet states, and the triplet state is always lower in energy than the corresponding singlet state. Next then is the HOMO to LUMO plus 1 excitation. That gives you the first triplet A2 state at 9.26 electron volts. And then, sorry, that's a mistake. That should be, sorry, that is actually the triplet A1 state at 9.41. Then you have the singlet A2 corresponding to this one, and the singlet A1, etc., right? So you see, the take-home lesson is that so you have a systematic recipe like to construct these many particle states from the one particle state. That's an incredibly approximate way of doing it, because in reality a many particle wave function is way more complicated than that. Way more complicated than that. It's far beyond the capacity of the human brain to understand a many particle wave function. So that is basically one relatively elementary approximation to it that we can wrap our head around it. But if we would calculate it exactly how I talk about it here, we would not end up with an accurate result relative to experiment, right? Okay. Let me give you just briefly, I don't want to go through that in great detail, but when you want to figure out the symmetry of the state, then you have to take the direct product. And that is very simple as long as you are in an abelian point group. That abelian point groups are those that don't have degenerate irreducible representation, because then the direct product of two irreps is always another irrep. Yeah? And so there are simple rules here, and then it's A times A is A, B times B is A times B is B. In D2H, like B1 times B2 is B3, and cyclic permutations of that, and you always have grade times grade gives grade, ungrade times ungrade gives grade, and grade times ungrade gives ungrade, etc. It's getting more involved if you are in non-abelian point groups, like cubic point groups, for example, that have degenerate representations, because then the direct product of two reducible representations is again reducible. And that is getting more complicated. I don't want to go into it, but one thing you find in your group theoretical tables is that you have, for example, that the direct product of t with another t gives you a1 plus e plus t2 plus square brackets t1. And the square brackets, that denotes the totally antisymmetric product. And the totally antisymmetric product is what you get when you have all spins of all electrons in that shell aligned. So that helps you finding the irreducible representations of the many particle states in degenerate point groups. It looks scarier than it is, so once you start going through the multiplets of the dn configurations in transition metals, whoops. Okay, so now when we construct these many particle states, there is that one thing I want to talk about, and that is the total spin. And in order to do that, we have to differentiate like three sets of many particle wave functions, or like three different types and representations of it. And so I told you already about a configuration that is just a set of occupation numbers, right? And so you have your set of orbitals, and then you specify in a given state how many electrons are in each orbital, and that is a configuration. And the Slater determinant, that is an anti-symmetrized product of orbitals. And so where you have a string of orbitals, and they all have an electron either with spin up or spin down. Yeah, and so that's a very common representation that you have in quantum chemistry. And the thing with the Slater determinant is that it is an eigenfunction to SZ, so it has a well-defined MS, but not a well-defined S, right? So what I told you here is, that a proper wave function has to be an eigenfunction of the total spin S, yeah, and not only of the spin projection quantum number m. Okay, so and when you do your mass in the way, let's try this. When you do your mass, sorry. No. Okay. I hope that holds. So when you do your math in a way that you count up those two spins and say like, well, 1/2 plus 1/2, that gives me 1, that is not giving you S, this is giving you M, right? But in order to get S is way more complicated, and that is what I want to talk about next. Yeah? So a Slater determinant then is a valid representation of a wave function that's an eigenfunction of SZ, but not to S squared. But you can take a bunch of Slater determinants belonging to the same configuration and then construct something that is called a configuration state function, or CSF. And the CSF is a wave function that corresponds to a single configuration but has a well-defined S and M sub S. And the easiest way to represent such a wave function graphically is the so-called spin branching diagram. And that is not something that people normally run into their chemistry curriculum, but I wanted to briefly bring that to your attention so that you know how that works. So on the x-axis you have a running number of that is counting the unpaired electrons. So in this case, say we have 4 unpaired electrons, and then the x-axis goes from 1 to 4. And on the y-axis there is an intermediate total spin. And so you start at the origin and have the first electron, and the first electron must always be spin 1/2. Now you add the second electron, you have two choices. You can either couple it parallel to the first electron, then you go to a total spin of 1, or you can couple it anti-parallel, and then you have a total spin of 0. And so on. Then the third electron, you can either couple parallel or anti-parallel, etc. And so you walk through that branching diagram and you end up at a given final total spin, and that might be the one that you want, right? And that is a graphical way to represent a spin eigenfunction belonging to a single configuration, right? So these are the SOMOs of your electronic configuration. So and obviously there are many ways to walk through that branching diagram, right? So in this case, I have a configuration where the first 5 electrons are coupled in parallel and the next 5 are coupled in antiparallel. So that would be the kind of situation that you meet, for example, in an antiferromagnetically coupled transition metal complexes. So, for example, you would have 5 orbitals belonging to your iron on the left side, and the next one are the 5 d orbitals belonging to the iron on the right side. And so that walk through the branching diagram will then represent like the antiferromagnetic CSF that is describing that system, and it's still a single configurational wave function, right? But obviously there are many pathways that you can take through that branching diagram in order to arrive at a given total spin, and that is not just like some arbitrary theoretical cruelty like designed to make your life miserable, but it is actually happening, and all of these states are physically observable. They're all there, right? And so you have, if you take it serious to understand like how electronic states work in open shell systems, you have to go through this. Yeah. And of course the mathematicians have worked out how many like walks you can take through that branching diagram to arrive at a given total spin, and that number is called FSN. So where S is the desired final total spin and N is the number of unpaired electron, and it's just that difference between the two binomial coefficients here. Yeah. So, and here is a little table that tells you how many, for a given number of unpaired electrons and a given total spin, how many determinants are there and how many CSFs, right? So for example, here for 10 unpaired electrons and a total spin of 0, you have 252 determinants that all have m sub s equals 0, and you have 42 possible CSFs, right? Etc., etc. So normally it's a very good idea to work with CSFs instead of determinants, because the total spin is a good quantum number, and that is a very good starting point for your electronic structure treatment. That's why within almost everything that you have in ORCA, we work with CSFs and not with determinants. Here's then an example of how that looks like, and let's just take this simple example where you have 3 unpaired electrons and a doublet state, and so that creates 2 doublet states. And one of them is called a sing doublet, and the other one is called a trip doublet, right? And so they correspond to that walk through the branching diagram, plus, plus, minus, and plus, minus, plus. So plus, plus, minus is first electron and second electron are coupled parallel, and then the third one is coupled antiparallel. So if you think you had just like a normal doublet state and you study the excited states of it, and you have moved one electron out of this orbital into an empty orbital and like retain the singlet coupling, that is a sing doublet state, right? And the alternative is that you move that electron, flip its spin, and at the same time flip the spin in the SOMO, and that is the so-called trip doublet. Yeah? So it's called a trip doublet because the excitation is a triplet excitation, and you couple that to a final state that is a doublet. Yeah, and so in terms of Slater determinants, they have, you see that this is more than one Slater determinant. The sing doublet is a 2-determinant wave function, and the trip doublet is a 3-determinant wave function. They all still want one and the same electron configuration, right? And so that is a take-home message. Then even if you find all of this confusing and complicated, like a single electronic configuration creates more than one many-particle state in general. Yeah. And here's an example from real life where you had observed such sing doublets and trip doublets. That is a cobalt complex that has a central cobalt spin 1/2, cobalt 2 spin 1/2, and 2 radical ligands. And so the analysis of that very rich absorption and MCD spectra led us to conclude that here band 3 is a trip doublet and band 8 is a zinc doublet. And so in real life spectroscopy, these things arise. And it doesn't matter whether you like it or not, it's just there. And so proper assignment means that you have to know these things. Yeah? Not all transition metal complexes are that complicated, but it's not uncommon to meet that kind of complication. And then you have to aware that you cannot just point to each and every peak and say that this orbital and that's orbital and that's another orbital, because at the end of the day you observe states. That is essentially the the one message that I wanted to give you with all that lengthy detour. Now let's talk about transition intensities, and in order to do that we have to briefly talk about the anatomy of a light wave. So that is a light wave, and it has a certain propagation direction, and each light wave has an electric component E and a magnetic component B that are orthogonal to each other and also perpendicular to the propagation direction. Yeah? And so that is the wave vector. Light has a momentum, and that is the momentum vector that's related to the wave vector k, and it also has an angular momentum that's 1/2 h bar. Yeah, and funny enough, the pure angular momentum states of photons are circularly polarized photons. Right and left circularly polarized photon, and linear polarization in a light wave is a linear combination of right and left circularly polarized photons. So that is is an aside. Now, when a light wave hits a molecule, the electric and magnetic field components of the light wave start interacting with the electrons in the system. Yeah? And that is inducing transitions between the many particle states. And now I've labeled them here as 0, S, M, gamma, according to everything I've told you before. And now the probability of absorbing that photon, that to first approximation, and that first approximation is known as Fermi's golden rule, is given then by the interaction of the initial state, most of the time the electronic ground state, and the final state, and then that Hamiltonian here, that is describing the interaction of the light wave with the electrons in the system, and then you take the square of that, yeah, because that in general is a complex number, and then you take the square of it, you end up with something that's real, and that gives you, that is proportional to the intensity, and that holds throughout all domains of spectroscopy. Now there are several mechanisms here that give rise to intensity, depending on what the interaction between the electrons and the light wave are. And in principle, there is unique and complicated, mathematically complicated interaction between light and matter. And what we know as the electric dipole, magnetic dipole, and electric quadrupole intensities, that comes from a divergent series expansion. I go into that later, but in ORCA you have the opportunity to calculate exact transition moments. And so that is what you find in the input as exact semi-classical intensity treatment. That is the exact light-matter interaction. And what you know probably from your lectures here, or that you had in chemistry or in spectroscopy, are the mechanisms concerning the electric dipole, the electric quadrupole, and the magnetic dipole interaction. So here's the electric dipole operator, that is just a sum over the coordinates of the electrons and the nuclei multiplied with the nuclear charges. And so that is interacting with the electrons and gives rise then to the electric dipole oscillator strength. And the electric quadrupole is then just simply the quadrupole moment, and it gives you an intensity expression that is proportional to alpha squared, and alpha is the fine structural constant, and the fine structural constant in atomic units, it's 1/137, right? So alpha squared is on the order of 10⁻⁴. And at the same time, you have the third power of the transition energy, whereas the electric dipole is the first power of the transition energy. And that means that these electric quadrupole transitions are extremely weak unless you're very high in energy. Yeah? And so that's why electric quadrupole transitions are, for all intents and purposes, only sometimes observed in X-ray absorption spectroscopy, but almost never in UV visible spectroscopy. Now, magnetic dipole transitions, that is the interaction of the magnetic part of the light wave with the electrons in the system, and that has an orbital part and a spin part. These are transitions that you see in EPR spectroscopy. So EPR spectroscopy is a magnetic dipole transition. And in optical spectra, these are also extremely weak transitions that you basically don't see. Yeah? So this is what you have in EPR. But so in the visible region of the spectrum, basically all of it is electric dipole intensity. And in X-ray absorption spectroscopy, I'd say 95+% is still the electric dipole that that is doing it. Yeah. Okay. Now you have a spectroscopic selection rule, and here you can use group theory, and I'm sure that Serena has talked about it. And the first selection rule is that the initial and final states must have the same total spin. That is a pretty strong selection rule, at least up to the end of, say, the first transition row, right? And after that, spin-orbit coupling is mixing states of different total spin, and that relaxes this transition, this rule. But so, say for organic molecules, first row transition metal complexes, spin-forbidden transitions have intensities of perhaps 1 per molar and centimeter, whereas allowed transitions are 3, 4, 5, 10 orders of magnitude more intense. Yeah? Then the second selection rule is the spatial selection rule, and that states that the direct product of the initial and final state wave functions and the components of the dipole operator must contain the totally symmetric irreducible representation. That's a relatively weak selection rule because there is a whole laundry list of mechanisms to break that, but it's a very good first orientation. And since there are 3 components to the electric dipole operator, and if you look into your group theoretical tables, these are the ones that are listed in the columns as X, Y, and Z, you can figure out what the polarization of the transition is once it's allowed. Yeah? So that is a spatial selection rule. So an electric dipole operator transforms as X, Y, Z. And if there is a center of inversion, then you have to have only allowed gerade to ungerade or ungerade to gerade transition. That is the Laporte selection rule that, for example, applies to octahedral transition metal complexes, but not to tetrahedral transition metal complexes. So under the Laporte rule, any DD transition in an octahedral transition metal complex is forbidden by spatial symmetry. That's why DD transitions tend to be weaker than, say, LMCT transitions. Yeah? If you want to find the selection rules for the magnetic dipole transition, so the magnetic dipole transforms as the rotations in the point group, Rx, Ry, Rz, and the electric quadrupole transforms as x squared, y squared, z squared, and the product of the coordinates. So all of that you will find in your group theoretical tables. So the next one I want to explain to you, that's really important, because I think that's also something that's often is associated with a lot of confusion, and that is the difference between a transition moment and a difference density. And let's look at this simple example. Say we have the pi system of the ethylene molecule, right? So we have 1 pi orbital and 1 pi star orbital. Now, the transition intensity I told you is the square of the interaction of the dipole operator between the initial state many-particle wave function and the final state many-particle wave function. So and you can visualize that since that is a multiplicative operator, so the integrand here is the product of the initial state and the final state. Yeah? Whereas the density of the initial state is psi naught squared, and the density of the excited state is psi 1 squared, right? So you see that this transition density is a totally different quantity than the ground state density or the excited state density. That obviously by construction is always positive, that is always positive, but that product can be positive or negative. Yeah. So what we have then is the dipole moment of the transition density, and the dipole moment of the transition density is different from the difference of this density and that density. Yeah. So the ethylene molecule obviously has no dipole moment in either the ground state or the excited state, right? So that is the approximate ground state, that is just like the doubly occupied pi orbital, and that is the excited state that that is, for just simplicity, just the occupied pi and the occupied pi star orbital. Neither of them have a dipole moment. But now the transition state density, the transition density, that is a product of the initial state and the final state. And so you can work that out by the Slater-Condon rules, that this matrix element reduces to this, namely the product of the pi and the pi star orbital with the electric dipole operator. And now it's a simple graphical game. That is a pi orbital, that is a pi star orbital. And now we can multiply these two together, right, in order to get the transition density. So let's do that. You have minus times minus gives plus, plus times plus gives plus. Minus times plus gives minus, plus times minus gives minus, right? So all of a sudden, this is then the transition density, the product of the pi and the pi star orbital, and that obviously has a dipole moment that is pointing along the CC bond direction, right? And so I hope that this illustrates like how a molecule that has no dipole moment still can have very large transition dipole moments in its electronic transitions. Yeah, so you shouldn't confuse these two. That it's very important to understand that. Yeah, and so for example here for an LMCT transition, so you see that is then the visualized transition density, and that is the visualized difference density that I've already showed you. Right? They kind of happen in the same region of space, right? Then it's here along the metal ligand axis, but they have very different shapes. Yeah. So the difference, the transition density and the difference density is very, very useful. I wanted to briefly bring one thing to your attention that I think is very useful when you start assigning optical spectra, and that is available throughout ORCA, and these are natural transition orbitals. Because what you can take now, if you say you have a complicated many particle wave function, or you have you have a TDDFT state that looks very chaotic because each state has 15 contributions from different orbital pairs, and then you say like, what is it that I'm looking at? And then it's very useful to take the transition density and calculate from it what's so-called natural transition orbitals. And these natural transition orbitals, they basically allow you for each and every state to identify a pair of orbitals that act as the donor and the acceptor for that transition, and that essentially allows you, no matter how complicated the wave function is, to visualize the transition as a transition between orbitals. Yeah? Now these natural transition orbitals, they may or may not look similar to some orbitals that you find in your ground state calculation, right? But essentially what you can get out of that is the assignment of each and every state in terms of orbital pairs. Yeah? For example, that is a simple copper complex, that is a singly occupied orbital in the ground state, and now you can calculate the natural transition orbitals here, and you find that this first excited state here has 14,000 wave numbers with an oscillator strength of 2.6 times 10 to the minus 3, has a donor orbital that looks a hell of a lot like a dz squared orbital, and an acceptor orbital that a hell of a lot looks like your SOMO, and so that's a dz squared to x squared minus y squared transitions, etc., etc. Yeah, but you have to basically plot these pairs for each, generate and plot these pairs for each of the excited states. Yeah, and so So you basically, what the program is doing then is to go through all of these states that you request. So you have to request it in the input. You say either NTOs all, or you only give it a list of orbitals, and then it creates an NTO file for each excited state that you have. Yeah, and so in the NTO file, that is a GBW format file, and that means it contains orbital information that you can use to plot. And for example, here was the 7th excited state, and the 7th excited state, now the NTO analysis gives you that it has like 0.3% of that excitation, etc., etc., but 98.5% of that state, and that is given by that excitation orbital 58 beta spin to orbital 59 beta spin. That means you go to ORCA plot and you create cube files for 58 beta and 59 beta, and then you plot that, and these are your donor and acceptor orbitals. Yeah, that's the way it works. And almost always you have one strongly dominant orbital pair that is dominating the transition, and that is what you can visualize, right? So that is basically a shortcut that allows you to go from something that is complicated and not very easy to analyze or to interpret to something that actually is easy to interpret. Yeah, so then you go to ORCA plot and then you plot these things, etc. Yeah. Okay, let's briefly talk about band shapes. Now, as I talked about before, like most of the time when we analyze band shapes, we just fit Gaussians underneath the absorption envelope. That is, of course, not quite what's happening, because what's happening is the following. So you have a ground state potential energy surface, and so here you can visualize it along each and every normal mode of the system. And that has a certain number of vibrational levels, and as long as you're in the harmonic approximation, these are harmonic oscillator eigenfunctions. And then you have the electronically excited state, and the electronically excited state along each normal mode has a displacement delta. Yeah? That simply means the excited state has a different geometry. You can also, for example, just imagine you like transfer an electron from a bonding orbital to an anti-bonding orbital, then the excited state, that bond will lengthen, right? And the normal mode that is dominated by that stretching vibration of that bond that you have excited into, that will be displaced to longer distances. So that is your dimensionless displacement delta. And then, of course, you have also the vibrational wave functions of the excited state. Now, essentially what you get is not just one transition, but you get a transition from each of the thermally occupied or thermally populated vibrational levels from the ground state into each of the vibrational levels of the excited state, right? And that gives you a so-called vibronic progression. And the intensities of each of these vibronic bands here, that is proportional to the overlap of the ground state vibrational wave function with the excited state wave function. And it's clear, if there would be no displacement and I basically propagate this ground state ground level vibrational wave function, which just is a single Gaussian, then it would only overlap with the first vibrational level of the excited state, right? For zero displacements, because these vibrational wave functions are orthogonal. Then there wouldn't be a progression. There would be one single sharp peak, yeah? So the longer that vibrational progression is, the larger the displacement is in the excited state, yeah? So basically in the case where you have vibrationally resolved structures, you can deduce that excited state distortion from that vibronic progression. Or a different way to do that is to look at the resonance Raman spectrum, because the resonance Raman intensity is proportional to the displacement squared. That's why resonance Raman is so much fun, because it really gives you a lot of information about the electronics, not just about the vibrations. Yeah. Now, the individual natural shape. So if you go through your quantum mechanics and like time-dependent perturbation theory and everything, you will find that the natural line shape of every spectroscopic transition on this planet is a Lorentzian. Yeah, so that is the natural line shape for every transition. And a Lorentzian relative to a Gaussian looks the following. So the Gaussian falls off very steeply, and the Lorentzian has a far more pronounced tail. In practice, we almost never observe Lorentzian unless you go to like really high level, highly resolved gas phase spectroscopy because of inhomogeneous broadening, right? Then it's so because we always do spectroscopy on an ensemble, or almost, like I know there are some single molecule people here, but we almost always like do spectroscopy on ensembles of molecules, and each molecule individually in the ensemble has a slightly different environment, and that like changes the transition energies a bit, etc., etc., and that inhomogeneity leads to a broadening, and that broadening most of the time is a Gaussian broadening, and that's why once that is larger than the intrinsic line, which it almost always is, then the resulting overall line shape of the transition is a Gaussian. That's why we tend to fit Gaussians. And especially in X-ray spectroscopy, people sometimes use a mixture of Gaussian and Lorentzian, that's so-called Fock band shape. And if you have a vibrationally resolved progression, then that is usually following the so-called Poisson line shape. In the Poisson line shape, that is the envelope that you get over a vibrationally resolved progression. I wanted to give you like one real life example that is quite illuminating, I think, and that is the spectra of high spin D5 systems. That's so-called Tanabe-Sugano diagram, where you see that you have a sextet S ground state and then a bunch of quartet excited states. So these are all spin forbidden transitions with very, very low intensity. But what you see here is that there are a bunch of transitions, here sextet A1 to quartet T2 and quartet T1, that are relatively broad. Yeah? And then there are these states here and that are very sharp, and according to the Tanabe-Sugano diagram, they're quartet A1 and quartet E. And so why are these so sharp and these so broad? And here is actually comes in what I just talked about. So these quartet T1 and quartet T2 transitions, they arise from a de-excitation from an EG electron that is anti-bonding to the T2G orbitals, right? But the EG orbitals are sigma anti-bonding, and the EG orbitals are sigma anti-bonding, and the T2G orbitals are only much weaker pi anti-bonding, right? So you take an anti-bonding interaction away, and that means that the complex will contract in the excited state. And that gives you dimensionless displacement, and that gives you a progression. And that progression is broadening the band. Yeah? That's what you see here. But here, that sharp peak, that is an intra-orbital transition, where you take an electron in one orbital and you just flip its spin. So the configuration is still the same as a ground state configuration. That means it changes nothing in the bonding, and then you don't get a progression. You don't get an excited state displacement. You only have the overlap of the lowest vibrational levels. You get a sharp peak. Yeah, so these very sharp peaks that you sometimes have in transition metal complexes, they're indicative of these intra-orbital spin flip transitions. It's a very common feature. Yeah, you have it in most DN configurations. You have that, and the signature of it is these sharp bands. Yeah. So you see, it kind of all makes sense. It's not arbitrary, and it's not mysterious. All right. So let us talk a few more minutes on working on assignments, because there are a few things that you commonly see in the literature that I want to at least make a plea, so to say, not to do it that way. And so here's here's one of the bad things that you see happening all the time. So you have an absorption spectrum, and then you have a section in the paper that says experimental results. And then you say, all right, so the experimental absorption spectrum of 1 is shown in figure X, and you clearly observe that the dx squared minus y squared orbital is higher in energy than dxy, and there's a shoulder at 540 nanometer, hence the partial charge of the metal, whatever. And I don't see a partial charge here, and I don't see a dx squared minus y squared orbital either. So what these imaginary authors have done is to mangle fact and fiction. Yeah? And please do not do that, right? So the thing is, an experimentalist works for eternity. Whatever the experimental result is, has to stand forever. If the experiment is done properly, 100 years from now, somebody needs to be able to reproduce it, and within the stated error bars that you give them, must get the same results. However, the way we interpret it, we talk about, is changing all the time, right? Because we talk in terms of models, we talk in terms of something. And now, if you basically contaminate proper experimental observations with whatever prejudice you have that this might mean, you kind of like fog up the experimental results. And it's much better that you state, exactly as I told you in the beginning, you do a proper Gaussian resolution of that, you do your fits, you determine the oscillator strengths, you determine the band positions, you put that in a table and say, that's it, that's my experimental result, and then you start the next section and say, like, interpretation of the observation. Because then somebody can read your paper, take your experimental result, thank you for it, that you did that job so properly, and completely discard any interpretation that you might make, right? That's okay, it happens all the time, right? But so don't mix fact and fiction. Yeah? Separate that cleanly, then you do proper science. Yeah. Oh, sorry. That should have popped up here. Okay, the other thing that I see happening all the time, when people have a spectrum measured and one calculated, and then you see statements like that in the paper. Say the calculated spectrum, in parentheses 396 nanometers, is in excellent agreement with the experiment 435 nanometers. That is where that seriously comes from. I mean, seriously. So that is then, say, the calculated spectrum, and it has something at 396, and that is the experiment that has something at 435. But you cannot possibly claim, like, not possibly, that this is in good agreement with that. Then is, yeah, right? That so a proper analysis of the spectrum means, like, really working, like, through what are the experimentally observed bands, what are their intensity, what are their position, working through the orbitals, working through the electronic states, etc., etc. But like, you can't possibly just hit the enter button and then read a wavelength out of the output and say, I can compare that to the experiment. That is that means you have no respect for your experimental data. Then so please don't do that. Yeah. Okay, because that is really what you should have done, and that is, as I have explained now a couple of times, like, figure out what the molecular orbital scheme is, put in your electrons, excite your electrons, and from there work out what the electronic states are that arrive, what are their multiplicities, what are their symmetries, what are the allowed transitions, etc., etc., and try to get your hands on as many different spectroscopic techniques as you can. That's a lot of work, right? And I'm not blaming you if you don't want to put in that amount of work. It's not always necessary, but like, if you're serious about like interpreting optical spectra, you have to do that and not just press the enter button and believe everything the computer says, please. And this, yeah. Yeah, and then once you do that, that is the kind of result that you have. You have your bands, you number them, you give them labels, and then you can go to a table, and that is the current interpretation of it, right? And then maybe 20 years later, somebody like Hawaii walks into my office and says, that's all bullshit, and I have a different interpretation, and then we can talk about it, and that's okay, right? But separate the fact and the fiction and do your job properly. Okay, I think I've talked for long enough. There is a bit more now still in the lecture notes. There are now 3 versions of the lecture notes in there, and this because Dan didn't give me the delete authorization, and that's why there is optical spectroscopy, optical spectroscopy final, and optical spectroscopy final 2. And, and that's final 2 is the one that counts. Yeah. So if you have any questions about that, let me know. And I think we also would have a few more minutes now to answer your questions. And thank you very much.